Hi, I'm Bill Mould, and this video is about the cracking of bicycle rims. If you work in a bike shop, you see rims come in with cracks in them, and it's interesting to do a little bit of cause and effect analysis of that and start thinking about what might be possible to do to mitigate the cracking problem and cause it to happen much later in the life of a wheel. You can think of this as a technical paper that is released in video form, but it's very scientific, and I felt an obligation to make sure that the content was accurate. So I have had it reviewed by a number of peers, 20 or so people who are material scientists, physicists, and or mechanical engineers, and I have incorporated many of their comments and thoughts into the presentation. This treatment applies to aluminum bicycle rims. Carbon composite rims crack by a completely different mechanism. If we look at the statics of a vertically unloaded wheel, this is what we see, that we have tension on all the spokes, which is trying to pull the rim inward, and that is balanced by the outward force of the rim, which resists that compression. And if we look at this, we see that the sum of all of the tension on the spokes is equal to the opposing force resisting the compression of the rim, and the sum of all those forces is equal to 0. Let's just consider the tension vectors. As the wheel is loaded, the bottom of the rim pushes up, and the tension on the spoke at the bottom of the load-bearing zone decreases. I've done extensive laboratory testing of this. Here is the setup. These chains allow a big load to be put on the bottom bracket, such as this 240 pounds. About 153 pounds of that is actually loaded on the rear wheel. With this setup, I'm able to measure the tension on all of the drive side spokes and then rotate the wheel 30 degrees, do it again, rotate the wheel 30 degrees, do it again, so that at each position I have an average of 12 separate readings. After 144 measurements, each of the 12 spokes will have had its tension measured at each of the 12 positions on the wheel. The average of those is a highly accurate data point. An alternative method of measuring tension would involve affixing strain gauges to each of the individual spokes in each wheel, but that would have been cost prohibitive and unnecessary. Altogether, I collected over 2,000 data points on a variety of wheels with different combinations of rim extrusions, hole drillings, lacing patterns, spoke thickness, and spoke tension. In this paper, I will show you data on 2 wheels that are exactly the same except for their spoke tension. This is a low tension wheel, 798 newtons, or about 80 kilograms of force on every spoke. And we will compare that to a highly tensioned wheel, starting out with 1,273 newtons, or about 130 kilograms of force on every spoke. Other than the starting spoke tension, these wheels are identical. And we'll see what happens to the tension of the spokes when we put a load on each of these rear wheels. Each of the wheels that we will compare is made of Sapim spokes that have a constant 2 millimeter diameter. Looking first at the low tension wheel, we'll see what happens when it is put under a load. Under load, we see that the spoke at the bottom of the load-bearing zone has lost 54% of its tension. The spokes on either side have lost some tension, and all of the other spokes have gone up slightly in tension. Let's look at the geometry of this wheel. This vertical bisector divides the wheel into 2 sides, a right side and a left side. The right side and left side are mirror images of each other. Now, if I start with an unloaded wheel where all the spokes have identical tensions, then the vertical load acting directly along the vertical bisector cannot cause lateral tension changes on one side of the wheel that are different from the other side. The loading on the wheel has to be symmetrical, and in the idealized case, the right side and left side tensions will have to be mirror images of each other. So we know that the tension on this spoke here is going to go up at the top of the wheel, and the tension down here at the bottom is going to go down. In between those, these two will go up, but will go up by equal amounts. These will go up by equal amounts, and so on. These two here will decrease by equal amounts. Except for a little experimental error, which I will explain soon, these trends were followed in every wheel tested. One important point is worth emphasizing. Here, if I superimpose on my graph the hours on the face of a clock, and let's consider the spoke at the 6 o'clock position straight down. So I'm going to measure the tension on every spoke in that clock as it appears here. But then I'm going to rotate the wheel clockwise 30 degrees. So now the spoke, which is at 5 o'clock, becomes at 6 o'clock, and so on. Every spoke moves around. So on the face of the clock, every position that we see is visited by every single spoke. So at every position around the clock, what you see is the average of 12 separate measurements. Now, to make our diagram a little less cluttered, I'm going to remove these two tension vectors. The tension changes here on the right represent some really very good data, but it's not exactly the same as we might have expected from the idealized result. These two spokes at the 11 o'clock and 1 o'clock position both went up in tension, and these two spokes at the 5 o'clock and 7 o'clock position went down in tension, but in both cases they are not exactly equal changes. Here I'm measuring the tension on the spoke at the bottom of the load-bearing zone, but as I move around the wheel to measure the tension on the other 11 drive side spokes, I have to hold the tensiometer in different positions and different angles, and that is going to introduce a little bit of error. Interestingly, even though the tension changes on all the spokes and is redistributed around the wheel, the total tension remains about the same. So on the loaded wheel, when we compare the spoke at the top of the wheel to the spoke at the bottom of the wheel, we see that there has been a change in the tension, or delta T, of 850 newtons minus 370 is equal to 480 newtons. Now we do a similar comparison before and after load of the high tension wheel. Here is our percentage comparison. We can see how the spokes change in terms of their percentage increase or decrease at each position of the wheel. Now, while it might be tempting to fudge the data here to make these numbers look a little closer to each other, I'm not going to do that because I gave you an explanation a minute ago, which I think suffices to explain why it is that these are a little bit different. And you'll see that in the big scheme of things, the thrust of what this paper will discuss in a few minutes, it's not significant anyway. Doing a side-by-side comparison, the wheel on the left has a total tension of 15,300 newtons. On the right, total tension of 15,622 newtons and a delta of 2.1%. This time looking at the graphic on the right, the high tension wheel, and we see that in the loaded wheel, we have a change of tension of 1,334 newtons at the top of the wheel to only 999 newtons at the bottom of the wheel, a change of tension, or delta T, of 335 newtons. One note is in order here. If you look at the graphic on the right, you see that some of the spokes that are not actually at the top of the wheel are a little bit higher in tension than the one that is. But I think that's a little bit of experimental error, and the spoke normally that is at the top of the wheel should be the highest. So that we see here that the range of tension of the low tension wheels is greater than the range of tension of the high tension wheels. Here is our equation for the modulus of elasticity. Sigma in the numerator is force divided by cross-sectional area, A0. And since the spokes are the same in both cases, sigma is going to be directly proportional to the force or tension. The change of stress in the low tension wheel is greater than the change of stress in the high tension wheel. What if I do the same comparison with different spokes? If I do the same experiments with double-butted spokes instead of straight gauge spokes, as you just saw, I get similar results. Once again, the change of stress or the stress range of the low tension wheels is greater than the change of stress or the stress range of the high tension wheels. Now, from this very technical book, Fracture Mechanics, I found a graph that appears to be right on point to our study. This graphic from the text shows a large plate with rhythmic changes in the stress field in the vertical direction, resulting eventually in a horizontal crack. Fatigue, of course, is brought on by repetitive stresses, and we're interested here in the stress range, that is, the difference between the maximum stress and the minimum stress. This is the same graph, except I have relabeled the lines as they would apply to bicycle wheels and alloy rims. This is the point in the life of the wheel that a micro crack develops and begins to propagate. There are two very important observations that could be made. First, if you look at the solid line, you see that the crack length develops more slowly. So as the number of cycles increases, the highly tension wheel develops a crack much more slowly than the low tension wheel with a high stress range. And the second observation is that in either case, when a critical crack length finally forms, in the case of the high tension wheel with low stress range, it develops later and at a longer critical crack length. Now we have to use some common sense here. If a manufacturer has a recommended tension limit of 120 or 130 kilograms of force, and you build a wheel with 200 kilograms of force, thinking that it will even further delay the onset of cracking, you're making a mistake, and you can actually see static loads cracking the rim. So let's keep in mind that there are limits to the amount of tension that a rim can stand. Let's delve into this a little bit deeper, and I'll show you some photos of some cracks that are admittedly anecdotal information, but maybe will lead to something. Almost all rims, be they carbon, composite, aluminum, or even wood, have what we call a stagger pattern from the valve hole, which here is covered up by a piece of electrical tape. And as we go clockwise from the valve hole, typically we see what's called a down-up stagger pattern. If I insert aluminum rods into the holes, this is what I see. So these holes are angled sideways one direction or the other. These two spokes are down spokes. On the top we have up spokes, and it continues all the way around the rim the same way. So going clockwise from the valve hole, we have a down hole, an up hole, a down hole, an up hole. But those slight changes of angle from side to side do not include any fore and aft angle of the hole, and that causes problems of the angle of the nipple and the spoke. Here's a bicycle rim. There is the spoke bed, the tire bed, the hole through the spoke bed, and the hole through the outer wall that the nipple is inserted through. If we look down on the rim from the inside, of course, we see the rim here with a hole in it. We bring a red sphere up to the hole from underneath. And if we expand this area, we see this picture. The sphere is making contact with all 360 degrees of the hole in the rim. Let's turn the sphere into a nipple. Now this is a CAD drawing of a supine polyaxial nipple, and what I want you to observe is that between these two lines here, the curvature is exactly congruent with the circle. The contact point of this nipple with the rim is going to be very near this line here. Here's another CAD drawing of a supine polyaxial nipple, and contact points between the nipple and the rim. So let's zoom into this and see what happens when the nipple has to angle or articulate itself to go with the direction of the spoke. We'll start by looking at some idealized views. So we see this picture here. Now if the nipple has to articulate to the left, we see this. If the nipple has to articulate to the right, we see this, but still in all three cases, we have 360-degree contact with the spherical part of the nipple with the sides of the hole. The contact between the rim and the head of the nipple is acting like a ball joint. Let's compare the CAD drawing of the supine polyaxial nipple with the CAD drawing of another nipple which is not polyaxial. Unlike the nipple on the left, the nipple on the right is not fully congruent with the circle, and you see that there is a gap there where the nipple has to make contact with the rim. When the nipple is angling straight out, we still have 360 degrees of contact between the nipple head and the hole in the rim. Let's zoom in here and see what happens when the nipple has to articulate to the left. We have a contact gap right here. When my nipple articulates to the right, we have a contact gap here. Here is a spoke which is angling toward the right and heading toward the right side of the hub hole flange circle, as you can see in the graph at the top. So we have an angle here of less than 90 degrees. For the purpose of illustration, I'm going to exaggerate the non-polyaxial nature of this particular nipple as shown here. The tension on the spoke is a force pulling the spoke and the nipple up. I have contact here, and over here I have either no contact or certainly less. This part of the rim here is under compression. This part here is under tension, resulting in a stress concentration point here, which through rhythmic fatigue cycles will result eventually in a crack. As predicted, when the spoke is angling toward the right, the crack appears on the left. Another spoke angles to the left and aims for the left side of the hole flange circle, so now we have an acute angle on the left, which makes my nipple articulate, so now I have a stress concentration point as we're looking at it on the right side of the hole. And that's where the crack is. It's on the right side of the hole. Very interestingly, where the crack begins here, it begins just on the surface, but as the crack extends, it also becomes a through crack. Regardless of where the crack initiates, it eventually extends to the other side also. And the crack will show some branching in advance of actually pulling completely through the rim. Let's delve into this a little bit more. Here are the shapes of the rim and the cross-section of the rim, and we're now going to allow the rim to get larger and larger. Now just focusing on this section here. In the limit, the rim becomes flat. And here are two perhaps better images of the rim and the cross-section. We make a hole for the nipple. Attach spokes and put some tension on them. As the wheel spins, cyclic fatigue cycles are loaded on the rim. Fatigue cycles operate in this plane also. This cyclic loading of the rim tries to pry open the hole. But there is a difference in the radius of curvature of the rim as seen on the left and as seen on the right. The radius of curvature of the rim seen like this is huge and amounts to the same thing as the radius of the wheel. The radius of curvature, however, of the cross-section is very small. Comparative values of perhaps 300 millimeters to perhaps 13 or so. The prying force on the hole is more concentrated in the picture on the right than it is on the left. Now this is not that easy to understand, so let's look at it from a different perspective. Here's the rim, and we will greatly expand this portion of the cross-section of the rim, so that we have this, where this hole here becomes this hole shown with a little bit of transparency, and we want to look at the curvature specifically of this point and this point. And what follows is a little demonstration where I put a BB in the top of one of the holes. What I want you to see is this, that when the BB is displaced at all in either of these directions, it will quickly roll back into the hole and stop. But when it is displaced in these directions, it will roll back into the hole, but it will oscillate back and forth.
Okay. Good.
And like this. Just fold it right back in. Put it this way though, it oscillates. Cool. We've seen that the downward curvature of the rim in this direction is greater than the upward curvature of the rim in this direction. Think of the metal in the rim being slightly saddle-shaped in the area immediately around the hole. Interestingly, a saddle point is known to students of multivariable calculus as an intersection of two differentiable functions. But don't be too scared by that statement. Look at the green point, that is the hole in this graph. From the front of the saddle to the back, the saddle point is the minimum of that function. But from side to side, that is where your legs would go, the saddle point is a maximum of that function. You can perhaps easily see the similarity of the saddle shape of the graph to the saddle shape of the rim. So depending on the curvature of the rim, instead of having my idealized contact with the hemispherical shape of the ball with 360 degrees of the circular rim, I may actually have primary contact points like this. The prying force is actually a function of the unevenness of the contact surfaces between the rim hole and the nipple that result from the small radius of curvature. Looking down on the hole from the inside, the force is more concentrated on these sides of the hole than on these sides of the hole. This is our textbook graphic of the stress cycles being applied vertically, resulting in a horizontal crack. And in the case of our rim, we see the hole, and once again, the dominant stress field is in the vertical plane as shown, resulting in a horizontal crack in the rim. We saw that a crack forms here from a stress concentration here, but the crack causes the rim to bend up slightly. The nipple pulls up from the tension on the spoke, and now the stress concentration is on the right side, resulting in an eventual crack there. In the same way, if I have a crack on the right side of the nipple, from this stress concentration, the rim bends up slightly. The nipple is pulled up again by the tension on the spoke, and the stress concentration moves to the other side. This development of cracking is actually a thermodynamically favorable change. There's quite a bit of potential energy that is pent up in the spokes, and some of that is released as the tension of the spoke goes down, coincidental with the development of a crack. So a small amount of energy is released as heat into the environment from the system. Some small amount of potential energy is also going to be released in the form of increased entropy. Now, it's all well and good to understand the mechanism of cracking, but learning how to delay or prevent cracking would be interesting too. So in the near future, 3 of us will be undertaking some significant testing in the Velocity Laboratory in Grand Rapids, Michigan, based on the following preliminary analysis. Once again, here is a supine polyaxial nipple. We insert the nipple into a rim and observe the very, very small contact points. If we take the nipple out, we observe a very, very tiny ring where the contact point is. The area of this contact ring is very, very difficult to measure, but it almost certainly is much less than 1 square millimeter. So what might be helpful about using a supine MG washer? Let's first look at its dimensions. Here is a CAD drawing of the washer with the dimensions shown. The hemispherical shape of the nipple is congruent with the shape of the washer. Now let's drop this nipple-washer combination into a rim. Note that the head of the nipple itself does not make contact with the rim, but the washer does. And the contact point is away from the corners of the hole. And in this case, the area of contact between the washer and the rim is 5.8 square millimeters. So a reasonable hypothesis is that the use of the MG washer would delay the onset of cracking in a rim. The plan is to build 6 test wheels. The wheels will be identical, except that 3 of them will have MG washers and the other 3 won't. So we have Velocity quill rims here, 6 Velocity race hubs, and Supeme is donating for the experiment spokes, nipples, and washers. Here is a cross-section of the quill rim. The quill rim is a suitable test rim because the bottom part, the spoke bed, is relatively flat and it's wide enough to be able to accommodate the MG washer and allow it to sit flat against the rim. It won't be perfectly flat because of the circular band shape of the spoke bed on the inside, but it will be pretty close. The 6 wheels then, one at a time, will be run on the laboratory of velocity on their drum, and we'll observe when cracks develop, as you can see in the following short clip. After that testing has been completed and analyzed, I will publish an addendum to this paper. Here's my contact information, and I will appreciate any constructive feedback.